Finally, it's time for the shortcuts. So we have seen the following. If we have the function f of x equals x squared, we saw that the derivative, which we will denote as f prime of x, equals 2 of x. Okay? We've seen that. We've also seen, if we start with f of x equals x cubed, the derivative of this is 3x squared. And we looked at Pascal's triangle as to how this pattern might continue. And then we also saw, very interestingly, if we start with f of x equals 4.9, it was t squared, we could have x squared, if we just treat it as x. The derivative here is 9.8x. Okay? And these are some derivatives that we've had, and we want to generalize this process. So how do we generalize this process? Consider f of x equals, let's just say it's x to the a, okay? X to some power, okay? What happens? The derivative, f prime of x, equals what? Well, it's like what happens with x cubed and x squared. You bring the number down and you lower the power by 1. So it's always going to be ax to the a minus 1. Okay, that is the derivative of any x to any power. Okay, this will also hold for negative numbers. Okay, so if you have negative numbers, what do you end up with? Okay, well, let's take a look. So if we have f of x equals x to the negative second, what is f prime of x? Meaning the derivative, which means the rate of change of that function at every given point on the curve, okay, or the slope or the tangent line. Bring down negative 2x and then subtract 1. If you do minus 1 from 2, you get negative 3. And do note that, that you could write this negative 2 over x cubed, right? Same thing. Okay, so what about this one, the 4.9? Well, we saw with limits, if you already have something there, you can basically pull it in front, right? So if we have f of x equals, let's say 3x to the fourth, what's f prime of x? Okay, it's the same as x to the fourth derivative times 3. So you're going to multiply the 3. So you bring down the 4, 3 times 4 is 12. It is 12x cubed. Now, what about constants? Okay, what if we have a constant? What if we have, I'm going to start to too many f of x. Let's say we have g of t equals 4. What's the derivative of g prime of t? I think we looked at one of these. Like, if it's always 4, if you want to make like a visual, you have a straight line, it's always 4. What's the slope of that line? It's 0. Okay, it doesn't change. So constants go to 0. Additionally, constants do fit into this general power rule here. And, you have x to the 0, right? So 4 times x to the 0, because x to the 0 is 1. Bring down the 0 and it becomes 0. Now we can combine these for any polynomial. Okay? So let's get up a polynomial. How about h of t? And let's consider 3x squared minus 2x plus 1. And we want to find what's h prime of t. Okay, it's a limit problem by definition, and you can distribute limits to individual terms. So the derivative of this polynomial simply uses the power rule on each of the terms. Okay, 3x squared. 3 times 2 is 6. Bring down 1 power, it's 6x. Negative 2 times x is just negative 2. Okay, the power rule does still work here. It'd be like 1 times negative 2, and then you subtract from 1 to get x to the 0. But people just, I think, tend to remember that when you just have an x, it goes away. So the derivative here is 6x minus 2. Now at this point, you should be able to take the derivative actually of any polynomial function, which is tremendous. Okay, there are some others. You're going to learn how to take the derivatives of all functions. So one of the more interesting derivatives is with exponential functions. And you might ask the question, which is related, is there a derivative that is the identity? And what that means is you take the derivative of some function, it gives you back the same thing. That would be like a function who's changing at its own rate. And what people found is that, exponentials appear to be close to doing this, but it looks like it's got to be an exponential between 2 and 3, closer to 3, slightly closer to 2.5, about 2.71828. It's e to the x. You will never look at e to the x the same. So if our function f of x equals e to the x, the derivative of e to the x is e to the x. Okay? I'm just giving this to you by definition. So this is tremendous. E to the x is actually the identity in calculus. Okay? It is going to be like your good friend, because when you have to do derivatives, and you'll become an expert at taking derivatives, of course you're always happy to see e to the x. Okay, so it sort of takes on a new status in calculus, and it is the identity. Okay, that is absolutely tremendous. Now, similar to e to the x, we have, what if we have f of x equals the natural log of x? Now, this is also a bit of a surprise. And once again, I'm just going to give it to you. It's actually 1 over x. So this is very interesting. Why do I think it's so interesting? This is x to the negative first, right? We just looked at x to the negative second. Okay, so if you look at like functions and their derivatives, it's kind of fascinating. X squared, how can we do this? If you have x to the negative, let's start with x to the negative second. X to the negative second goes to negative 2x to the negative third, right? What does x to the negative first go to? Okay, meaning when I say go to, I mean the derivative here, okay? So the derivative really is an operator. It operates on a function to deliver a new function, which is kind of cool. Well, we can do this now. We do negative 1 times x, subtract 1 to the negative second. So it's negative x to the negative second. And so what we have here is sort of like a chain. Okay, you kind of have a fascinating chain. Sort of in the bottom of this chain, you have kind of the higher powers. And so you'd have like x to the first just goes to, the derivative of that is 1. X to the second is 2x, and so on. And you have like all the powers of x except for x to the negative first. Right? Like, how do we get x to the negative first? What's the derivative that gives us x to the negative first? That's not a power, it's natural log of x. Okay? Natural log is log with base e. Okay, very cool. All functions have derivatives. Let's just go over maybe a few more. We actually have their trig functions. And so if, say, h of x is the sine of x, h prime of x is cosine of x. Okay? Beautiful symmetry. The derivative of sine is cosine? That's cool. Okay, what about the derivative of cosine? Now let me express this as an h double prime of x, because, it's a function. If I take second derivative, it's h double prime. And do you go back to sine? Almost. It's negative sine of x. So each of the trig functions when you take the derivative, it gives you another trig function. Just to give you maybe a couple more right now, what are some of the other trig functions that we can use? Tangent goes to secant squared, meaning that's the derivative. Tangent of x, secant squared of x. Secant goes to secant tangent. So secant of x goes to secant tangent of x. And there are others which we will look at later. But this is a really good sort of starting place to start to compute derivatives quickly. Because when you're doing calculus, the goal really is to be a practitioner of calculus. And what it means to be a practitioner of calculus is you want to be able to compute derivatives fairly quickly. So most of us who do calculus don't spend our time doing limits for a bunch of problems. We implement known shortcuts, kind of like I'm showing you here, that you can use. And so some of these you will memorize as you are working through, like sine is cosine, cosine is negative sine, e to the x is e to the x, ln x is 1 over x, tangent is secant squared. Others, like some of the other trig functions that are less common, like say cosecant of x, you will learn tools to derive. Now, one last piece about notation. Okay, so this notation, the prime, is due to Newton. Okay, it's a nice notation. Leibniz, considered co-creator of the calculus with Newton, had a different notation. And so let's look at what is his different notation. Okay, for a different notation, we need to have, let's put something up here. Let's use y. So how about y equals, and let's do, how about negative 2 over x? What's the derivative of this function? Now, I sometimes like to write denominators in terms of their powers because I think it's a little easier to then get the derivative. So if we write it like this. Now, if I look at the right side, okay, I take that derivative and I multiply the negative 1 by the negative 2. I get positive 2. And then I get the x to the negative second, which is the same as over x squared. So y prime would be the Newton style of notation. The Leibniz style, which we will use more of later, is dy dx. Okay? So this is a very suggestive notation. Dy dx means the derivative of y with respect to x. Okay? And so it sort of is providing a little more information, right? If we look over here at, say, the h, we have h prime of x. Okay, that just says it's the derivative of an x function. Okay? But dy dx says we have the derivative of y with respect to x. It's a little different. And this becomes more pronounced when you have lots of x's and y's, and when you have multivariable calculus, you could have a function of different variables, and then you could have, say, like dy dx, dy dt of the same function that could give you different derivatives. So there is not a universal notation for derivatives in calculus. And I will even give you one more. It's kind of like what I was doing up here. So let's look at it's the operator. Let's look at the derivative operator. Okay, the derivative operator, it sort of comes from the Leibniz. It's d dx of what? Of some function y, right? Okay, well, you put something in there. Okay, what haven't we seen yet? We've seen a lot. Let's put some of it together. What if we had 2 sine of x? Okay, what does this equal? Well, you're just taking the derivative of that, okay? And that would be the same as the derivative of sine x, but with the 2 out front. So it is going to equal to cosine of x. Okay, so this notation, less common in introductory calculus as an operator, is actually used widespread in quantum mechanics. You know, there aren't just differential operators, there are other kinds. New word, differential. What's a differential? Dy dx, those are considered differentials. Okay, I'm not going to go in depth about what differentials are, But note for now that a differential is considered like an infinitesimal change. Like, we had the delta x over delta t as delta t goes to 0, the triangles, right? The idea of delta t going to 0, like here that would be, say delta x going to 0, is that the x's are getting infinitesimally small. And so it's like, how does y change by a tiny bit when x changes by a tiny bit? Okay, more on that later.